Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problems 1 to 5 of the multiple choice AP Calc exam 012. Alright, let's take a look at question number 1. It reads, if y equals x sine x, then the derivative DUI DX equals what? So the tip you want to keep in mind for this problem is that you do not distribute the derivative across a product or quotient of functions. Okay? If you have a product or a quotient of functions, you use the product or quotient rule. But you can distribute the derivative across sums and differences. Okay? So let's take a look at the formula that will be guiding our problem solving process for today. So the formulas are, first one is the product rule, which you should have mastered before the AP exam. The product rule is, if you're looking for the derivative uv prime of two functions u and v, the derivative is v u prime plus u v prime. Okay? And then you need to remember your trigonometric differentiation rule. The trig differentiation rule that we are going to be using for this example is the derivative of sine. The derivative of sine x is cosine x. And lastly, the power rule. We're going to be applying that to the derivative of x, x prime equals 1. Okay? Now let's go ahead and solve the problem. We have y equals x sine x. So we have a product of two functions, the linear function x and the trigonometric function sine x. So what we're going to do is label them u and v. Okay, so the first function is u, and the second function sine x is v. Okay, so what is dy dx? Dy dx is equal to x sine x prime. Remember, prime and dy dx are the same thing. Okay, so let's see what we have. Applying the product rule, we'll have vu prime is going to be sine x for v times u prime, which is x prime, plus u, which is x times v prime sine x prime. Okay, now let's differentiate and simplify. Sine x times the derivative of x is just 1, plus x times the derivative of sine is cosine x. Okay? If we simplify, we'll have sine x plus x cosine x as our final answer, and that is option letter B. Now let's take a look at question number 2. Let f be the function given by f of x equals 300x minus x to the third. On which of the following intervals is the function f increasing? One thing you want to keep in mind is the connection between the sign of f prime and the behavior of f. If f prime is positive on an interval, then f will be increasing on that interval. Okay? So let's keep that in mind. Now let's write down the procedure for solving this problem. There are three parts to this process. Part 1 involves finding the critical values. Okay, so you find the critical values. What are the critical values? These are the x values where the derivative is equal to 0 or does not exist. Okay, after that, we're going to set up a number line sine chart. Okay, so set up a number line sine chart that will enable us to see how the sign of f prime changes across the critical values. And then lastly, we will find the intervals. Find intervals where f prime is positive. Okay, let's do it. Part 1, we want to find the critical values. So find the critical values. Basically where f prime is equal to 0 or does not exist. Starting with the function f of x equals 300 x minus x to the third. We're going to find the first derivative, f prime of x. Applying the power rule, the derivative of 300x is just 300. And the derivative of x to the third is negative 3x squared. Now to find the critical values, we're going to see where f prime of x equals 0 and where f prime of x does not exist. Okay? Since we do not have a denominator here, there isn't an x value where this function is going to be undefined. This is a polynomial function. It is smooth and continuous. Is differentiable everywhere. Okay, so all we just have to do is find where the derivative is equal to 0. This situation is not applicable. So we'll take the derivative and set it equal to 0. And let's solve this. We can subtract 3x squared from both sides and flip the equation. We'll have 3x squared equals 300. Divide both sides by 3. That yields x squared equals 100. And then we are going to take the square root of both sides. Now one thing you want to keep in mind is that anytime you take the square root of a square, you have to introduce the positive and negative roots. So plus or minus 10, because when you square 10 or negative 10, you end up with positive 100. Okay? Now we have our critical values. Let's list them. Our critical values are x equals negative 10 and positive 10. We are done with part 1 of the procedure. Now let's advance to part 2, which involves creating a number line sine chart. Let me partition my workspace here. Part 2 and 3 are basically combined in one. Okay, so we have our number line sine chart. We're going to graph the critical values on a number line. This will be an open interval because we do not have any constraints on the domain. Okay, so we're going to graph negative 10, and positive 10. Now let's put up some partitions so we can have a visual distinction as to what's going on where. Because we have two critical values, our sign chart will be divided into three regions. Okay? So in the first region, we're going to select an x value, basically an x value that's smaller than negative 10. Let's use x equals negative 11. And then in the second interval, let's call this 1. In the second interval, we're going to pick an x value that's between negative 10 and 10. X equals 0 will be a good option because it's easy to work with. And then over here, we are going to pick x equals positive 11 for interval 3. Now what we want to do is we want to use the sine of f prime to determine the behavior of f. Okay, so we're going to be looking for the sine of f prime and use that to determine the behavior of the function f. Alright, let's start with the first interval. So we are going to look for the sine of f prime. What we're looking for is f prime of 11. So we'll simply plug in negative 11, sorry. We will simply plug in negative 11 into the derivative function right here. So that is 300 minus 3 times negative 11 square. If we simplify that, we will have 300 minus 3 times 121, which gives us 300 minus 363. And then the difference is going to be negative, okay? So we have negative 63. That tells us that the function is going to be decreasing on this interval right here. Now let's take a look at interval 2, x equals 0. We want to look for the sine of f prime. F prime of 0 is going to be 300 minus 3 times 0 square. Using the order of operations, we have 300 minus 3 times 0, which is just 0. And we can see that f prime is positive on this interval. What does that tell us about the behavior of f? It tells us that f is increasing on this interval. The last one is from 10 to infinity. We're using x equals 11. So we're looking for f prime of 11, which is 300 minus 3 times 11 square. If we simplify, we will have 300 minus 3 times 121, which equals 300 minus 363. And we'll end up with a negative result again. So in this interval, the function is going to be decreasing. Now, what is our conclusion? Our conclusion is that, let's write it down. Conclusion: since the first derivative f prime is greater than 0 on the interval negative 10 to 10, then f is doing what? F is increasing on that interval. Okay, so our answer is going to be option letter B. That is where the function is increasing at. Now let's take a look at problem number 3. We are to find the integral of secant x tan x. Now a tip you want to keep in mind is has to do with the reversal of known derivatives. Now, if you know the differentiation rule for a function, then you automatically know what the related integration rule is by reversal. Okay? So the formula that we're going to be using for this problem is as follows. The derivative of secant x is equal to secant x tan x. Okay? Now, how does this help us with this problem? In this problem, we are asked to find the integral of secant x tan x. What is the relationship between the integral and the derivative? They are inverse operations, right? So since this is a derivative, by integrating this, we're going to end up with the antiderivative, which is secant x. So when we integrate secant x tan x, this is a known derivative. Okay? So by simply reversing this differentiation rule up here, we are going to end up with secant x plus c. Answer is option letter A. Alright, let's take a look at problem 4. It reads, if f of x equals 7x minus 3 plus the natural logarithm of x, then f prime of 1 is equal to what? Now, a caution that you want to keep in mind has to do with evaluating derivatives. Now, whenever you're evaluating the derivative at a point, you want to remember to differentiate first before you substitute. You never want to substitute and evaluate, then differentiate. That's incorrect. So you do your calculus first before you do your arithmetic. Now, these are the steps that I just highlighted in the cautionary steps that we went over. So the steps are, first you find the derivative, find f prime, and then secondly you evaluate the derivative at the indicated point. So f of x is equal to 7x minus 3 plus the natural logarithm of x. Step 1, we'll find the derivative, f prime of x. The derivative of 7x is just 7. The derivative of 3, using the constant rule, is 0. And the derivative of the natural logarithm of x is 1 over x. So if we simplify f prime of x, we'll have 7 plus 1 over x. Now the derivative at 1, we're now doing step 2, okay? The derivative evaluated at x equals 1 is 7 plus 1 over 1, which is 7 plus 1, and it gives us the answer 8. Option letter E is the correct answer for this problem. Alright, let's take a look at question number 5. It reads, the graph of the function f is shown above. So I have it right here. Which of the following statements is false? So one thing you want to keep in mind is when the double-sided limit exists and when it does not exist. Given a graphical representation, as is the case with this problem, the double-sided limit always exists at a point where a function is continuous, or a point where a function has a removable discontinuity. So if you have a scenario like this, at a point where the function is continuous across that point, or where you have a removable discontinuity. In these two cases, the limits will exist because the left and right hand limits will be equal to exactly the same y value. Okay? They're approaching the same y value as you approach these 2 points from the left or right. So let's keep that in mind. So what we're going to do is take a look at option A to D. They all have to do with the existence of limits. Since the problem asks us for which statement is false, let's see if maybe one of these limits is non-existent. Okay? If we do not find the answer here, we can take a look at option E and do the test for continuity. So the strategy that we're going to be using, let's write it down. Strategy is, we want to find where the limit exists. That's for option A to D. Limit exists when the left-hand limit is equal to the right-hand limit. Okay? Alright, let's take a look at option A. We'll start by identifying the points that we are approaching. We'll look at the left-hand limit and then the right-hand limit using the graph, and then we will see if the right-hand limit is equal to the left-hand limit. Okay, question mark. Now, for option A, we are approaching 2. So what direction are we approaching 2 from? There are no directions, so that automatically tells us that we are approaching from the left and the right. Okay? Left-hand limit is basically the limit as x approaches 2 from the left of the function. Now, what on earth is that? Given a graph, we are approaching 2 from the left, okay? So when you're given a graph, the graphical limit is basically the y value of the point that you're approaching. So this is the point, even though it's undefined, what is the y value of this point that we're approaching? The y value is 2. Right-hand limit as x approaches 2 from the right of the function. So if we're approaching 2 from the right, take a look at this point, this undefined point here. Or a removable discontinuity is more appropriate because it's actually defined. So as you approach this removable discontinuity, what is the y coordinate of this point? It's 2 also. Okay? So is the right-hand limit equal to the left-hand limit? The answer is yes. Limit as x approaches 2 of the function exists. Option A is correct. Alright? Now, based on what we just talked about earlier, as these two being the only cases where the limit exists, we can just look at the graph and we can easily determine what the answer is. If you look at 2, 3, 4, 5, 2, 3, 4, 5, do we have any cases where we have a discontinuity that's a jump or infinite or oscillating? The answer is yes. Take a look at option 4. We do not have a continuous function or a removable discontinuity there. We have a jump discontinuity, which automatically means the limit will not exist, and the answer will be option C. Okay, but let's go ahead and just show you the rest. So if we look at option B, nice little exercise on limits. X is approaching 3 from what direction? No sign is indicated, so it's automatically left and right. It's double-sided. Now, the left-hand limit, we are going to be approaching 3 from the left side. So graphically, we'll look at the point we're approaching, right, which is 3. We're approaching 3 from the left. If you're approaching 3 from the left, what is the y coordinate of the point you're approaching? It's 5, right? So there goes the answer. Now let's take a look at the right-handed limit. Limit as x approaches 3 from the right of the function. So we're approaching the same points because we have a continuous function from the right. What is the y coordinate of that point? And it's 5. Are the right and left hand limits equal? Yes. What does that mean? The limit exists and is equal to 5. Now option C, we said that the limit does not exist there because it's not continuous and it's not a removable discontinuity. We have a jump discontinuity there. So let me show you why the limit does not exist. Option C, we have x is approaching 4 from which direction? Left and right, bidirectional, right? Let's do the left hand limit first. Limit as x approaches 4 from the left of the function. So at x equals 4, coming from the left, what is the y value that the function is approaching? What is the y value of the point that the function is approaching? It's kind of like 1.9, right? A little bit below 2. So we have 1.9 for the left hand limit. Now let's approach 4 from the right. What is the right hand limit? Limit as x approaches 4 from the right of the function. Now you notice there is a jump. We have a different function now. We're now looking at this function that looks like a parabola. What is the y value of the point that you're approaching here? The y value is 4. That's the right hand limit. So is the right and left hand limit the same? The answer is no. So option letter C is a fail. This is the one that's false. Hence, that is our correct answer. Option letter C. Now, even though we have the answer, let's take a look at option D and E, okay? So for option D, x is approaching 5 from the left and the right since we do not have any direction stated. So x is approaching 5 from the left. Let's do the left hand limit first and see what it looks like. So we have this point right here. What is the y coordinate of the point that you are approaching? For this x value, the y coordinate that you're approaching is 6 from the left. So this is equal to 6. And then from the right, the limit as x approaches 5 from the right of the function is also 6. You're approaching the same point from the left and from the right. So that tells us that the limit does in fact exist. Option E is talking about something different. It's talking about continuity. It asks if the function f is continuous at x equals 3. So for continuity, let's write down the approach for that. For continuity, the left hand limit has to be equal to the right hand limit, and there is another condition. It has to be equal to the value of the function at that specified x value. Okay? So let's take a look at 3. What's happening at 3? At x equals 3, we've already shown that the left hand limit and the right hand limits are equal to 5. Okay? But what is the value of the function there? So for option E, we're looking at x equals 3. Okay, from the left and the right. So let me just copy down what I wrote earlier. The left hand limit of the function is equal to 5. The right hand limit as x approaches 3 from the right is also equal to 5. We need another condition. We need to find the value of the function. What is the value of the function at x equals 3? So all we are simply doing is evaluating the function at x equals 3. So what is f of 5? At x equals 3, what is the output? We can clearly see that at x equals 3, the output is 5. Okay? So f of 5 is equal to 5. Now, since the right-hand limit is equal to the left-hand limit and is equal to the value of the function, this automatically implies that the function is continuous at that x value. So we see why option E is correct. Is true. Okay? So one thing you just want to keep in mind is, even though a function has a cusp or a corner or a vertical tangent, the limit still exists. Okay? The only time when the limit fails is when you have a jump discontinuity, like right here, an infinite discontinuity like an asymptote, or an oscillating discontinuity. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming AP exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments about the contents of this tutorial or any AP Calc question in general, just place your question in the comment section below, and we will be more than glad to support you. Do not forget to subscribe to our channel for updates to other great test prep materials such as this. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.